Hello, hello, welcome. This week we're doing the Physics Week 3 lab. We're going to start with Activity 2 because Activity 1 is pretty easy and I have great faith in you. You can do it. All right. So, without further ado, let's jump into this. Activity 2. In this section, you'll draw the electric fields as several simple charge configurations. Okay? While you will be able to draw only a two-dimensional picture, keep in mind that these are inherently three-dimensional connotation there. For each case, draw the electric field lines, draw the Gaussian surface, and state whether the flux is positive, negative, or zero. All right. So I'm going to start by drawing a charge Q right here. That guy's going to be Q, specifically plus Q. And I have electric field lines going in all directions. Actually, it literally is going to have all directions. Excuse me. All right. So now we need to draw a Gaussian shape. I'm going to do a sphere because that's what they tell us to do. And it's going to be centered. Now we need to state if the flux is positive, negative, or zero. Okay. So the outside of the surface is here, and I'm going to draw the vector dictating the direction of the Gaussian shape, and it's going to be pointing outwards. Gaussian shapes are closed surfaces, like so cubes, spheres, melons, or whatever oblong type shape you could think of. So it's always going to they're always going to have an inside and an outside, and so the little squares can be pointing towards the outside, and the electric field at this point is also going to be pointing outward. And these two will be parallel to each other. So specifically, the angle between the two will be 0. So your next question is, why does that matter? Who cares? We care. That's who cares. So when we write up the equation, flux, by the equation I mean Gauss's law, we have Q enclosed over epsilon naught equals surface integral, closed surface, E dot dA. These are both vectors. So it's a dot product right here. So dot product means cosine. Because normally you think, oh, cross product, cosine, they both start with C. That makes sense. They were like, no, that's a trap. Don't fall for that trap. Dot product, cosine. And a cosine of 0, which is the angle between these two, is 1. Therefore, we'll have, 1 is positive, therefore the flux is going to be, this number here is going to be positive. All right, so another way to look at it is we have a positive Q enclosed. We have epsilon naught, which is also positive. Therefore, this number is greater than 0. Therefore, the flux is greater than 0. Therefore, positive. All right, understand? All right, going to follow the same procedure with all of these. All right, a charge, negative Q, when the surface is a sphere centered on the charge. All right, same question as before, except this time we're going to negative Q. Negative Q, fix that up a little bit, negative Q. So the arrows are going to point inward. I'm going to draw a sphere again. There we go. I think I just got to draw it slower. So this time we're going to have the E going inward. We're going to have the small section of surface area going upward. We're going to have Q enclosed over epsilon naught. And we're going to have a surface integral, E dot dA. All right, so the theta between these two equals pi, or 180. The cosine of pi is negative 1, so this guy's going to be negative. Q enclosed is negative. Epsilon naught is positive. So Q enclosed over epsilon naught will be negative. So we will have a negative flux. All right. So now Case number 3. That's kind of blood. There we go. I just zoom out a little bit. Looks less blurry. All right, a charge plus 2q when a surface is a sphere. Same thing as the first one, except now, same idea as the first, except now we have 2q. So with 2q, that means that flux equals q enclosed over epsilon naught. But now this q is going to be 2q plus 2q. So it's going to be exactly the same as the first one, positive, except the flux will be twice as much. Twice as much. How does this flux compare? It is twice as much flux. Twice the flux. There's going to be some great joke there. I'll think of it later and then say it later when people have already skipped ahead in the video and they'll totally miss the context. All right, case 4. Positive q charge when the surface is a sphere offset from the charge, but the charge is still inside the sphere. Okay. Now, this is where they start taking off the gloves. So we got a that is a terrible, terrible drawing, but you get the idea. Arrow starts here, goes out. These are electric field lines. So straight up Gauss's law again. Equals q enclosed over epsilon naught equals surface integral of E dot dA. Okay? So you look into this and it's like, man, well, so in some places, like, I can't think of a good spot here. Here, the electric field might be going this way, but since the charge isn't centered, the dA, the small section of area, they won't line up exactly. So theta will not equal 0, always. In some places it might actually equal 0. There's probably a mathematical way of finding which place will equal 0. It's probably like, I don't know, 2 or something. But when you consider an infinite number of pieces of dA, then 2 divided by infinity is small and negligible. So this equation right here becomes really hard to evaluate, and we're not going to. But what we are going to do is we're going to look at this q enclosed here and be like, oh, this is positive, that's positive, positive over positive, bam, positive. And we can even calculate the flux if we know what q enclosed is. So the idea here is it doesn't matter that it's off-centered. If it's off-centered, it just means that we can't use this, can't easily use this equation anymore. We just go straight q enclosed. Be like, oh, q enclosed, call it good. How does this flux compare to the flux in case 1? The same. Bam. All right. A charge plus q when the surface is a sphere offset from the charge, so the charge is outside the sphere. All right. Hope. All right, so we have q enclosed. No, we have a q right here, positive. It shoots off electric field lines in every which way. Specifically, it's going to shoot them into the sphere, Gaussian sphere, making some flux, but then it's going to shoot out the other side of the sphere, losing some flux. So the idea is all the electric fields that enter are also going to leave. Therefore, the net electric flux is going to be 0. Another way to look at this is we have our equation, the same one we have used every single time. Epsilon naught equals integral surface enclosed E dot dA. Again, not all the EAs are related in the exact same way, or not all the electric field lines are exactly related to the small sections of area in the same way. So specifically, like the angles between them we know aren't going to all be the same. So this equation right here is of minimal value. But we do know that there is no charge enclosed in this Gaussian shape. Therefore, 0. So 0 over epsilon naught is 0. So there is 0 flux. 0 flux given. All right. See, I just played that off like it wasn't a joke, but it really was. That's how you can get things. You can say really funny things in a professional setting, as long as you pretend it wasn't a joke and you're just being dumb and oblivious. A charge plus Q when an irregular surface surrounds the charge. All right, so we got our plus Q right here, and we're gonna have right here. And we have the funny shape, but we know that it is a closed surface. Oh, sorry, make that a big A. So looking at flux, just rearranging the equation a little bit, making life making life interesting. All right, so we have a Q here. We know that it is enclosed. It's positive, so it's shooting out electric fields willy-nilly. I say willy-nilly, but there's actually, probably in a very uniform manner. So Q enclosed equals positive Q. Epsilon naught is a positive, therefore positive flux. All right. How does the flux compare to the flux in case 1? The same. How does flux compare? Yep. Same flux, because all we're looking for is Q enclosed, epsilon naught, and flux. So Q enclosed is going to be the same. Epsilon naught is a constant, so it will always be the same. And then therefore the flux will be the same. An electric dipole made of positive Q and negative Q in a surface that encloses positive Q but not negative Q. Okay, they're trying really hard on this one, and I will give them that. What color was Washington's white horse? It was white. All right, same concept here. Flux equals Q enclosed over epsilon naught. Interesting. Equals surface E dot dA. All right. So Q enclosed is positive Q, and epsilon naught is epsilon naught. Again, because of the negative Q, because these aren't necessarily centered and it's not uniform, it's going to be hard to do this integral, so we're not going to use it. But we know what Q enclosed is positive. Therefore, because as I said earlier, all the negative Q's, electric field lines with negative Q are going to both pass in and out of the shape. So the negative Q will have no influence. So the positive Q, though, Q enclosed over epsilon naught, it'll be positive, therefore positive. And they're probably going to ask, how does this compare to number 1? It is exactly the same as number 1. Ooh, it even does specifically. Oh, man. How does this flux compare to case in number 1? The same. Explain. And I would explain by just writing this right up here, where we have Q enclosed over epsilon naught equals Q enclosed over epsilon naught. Bam. Therefore, the same. Based on your conclusions in the 7 examples that you have just studied, what is a plausible but not proven relationship between the flux and the charge enclosed by the surface? Okay. Well, maybe they weren't expecting us to use Gauss's law with the exact information that they taught us. But I'm going to say a relationship might be that flux equals Q enclosed over epsilon naught enclosed, which equals E dot dA. What they really are probably looking for is flux is proportional to Q enclosed. All right? I think that's all for this first part. Yes, I'm going to say that's all for this first part, and that we won. Huzzah! On to activity 3.